Have you ever looked at a math problem, all those X's and Y's, and felt like you're trying to crack some kind of secret code? Well, guess what? You kind of are. And today, we're going to crack it together. We are decoding one of the most important concepts in all of algebra, polynomials. So here's the game plan. First, we'll figure out what a polynomial even is. Then, we'll take one apart to see how it works. After that, we'll learn the secret names for them. And finally, the really cool part, how to find their zeros. Sound good? Let's dive in. All right, let's jump right in. Section 1. What is a polynomial anyway? I mean, before we can play the game, we've got to know the rules, right? So let's see what it takes for an expression to officially be called a polynomial. Okay, I know this looks like a textbook definition, but don't worry, it's way simpler than it sounds. Think of it like this. A polynomial is just a bunch of variables, like x or y, and some numbers, which we call coefficients. And they're all just strung together with plus, minus, or times signs. But there is one super important rule in there that changes everything. And here it is. This is the number one rule, the one you absolutely cannot break. This is what separates a real polynomial from all the fakers out there. Seriously, if you remember just one thing from this part, make it this. It all comes down to the exponents, the little numbers up top. For an expression to be a polynomial, the exponents on the variables have to be non-negative integers. What does that mean? Simple. No fractions, no decimals, and definitely no negative numbers up there in the power. It's got to be clean, whole numbers like 0, 1, 2, 3, and so on. That's it. Let's look at some examples to make this crystal clear. Over on the left, you've got your A team. These are real polynomials. See how the exponents are all nice, whole numbers? And hey, you might see that square root and think, wait a minute, but look closer. It's on the number, not the variable. So that's totally fine. Now, look to the right. These are the imposters. That square root of x, that's really x to the power of 1/2. So, nope. And 4 over x, that's the same as 4 times x to the power of -1. So that's a big nope too, not polynomials.
Awesome, so now you're a polynomial spotter. You know the real deal from a fake. So what's next? Let's grab one of these things and, like a scientist, put it under the microscope. We're going to dissect it and figure out what all the different parts are called.
And here's the one we're going to work with. Let's use this example. 7x cubed plus 4x squared minus 3x plus 12. Let's break this thing down. First, let's talk about terms. What are they? They're just the individual pieces of the polynomial that are being added or subtracted. So if you look at our example, the terms are 7x cubed, then 4x squared, then that minus 3x, and finally the number 12. 4 separate terms in total. Okay, so within each term, see that number right out front next to the variable? That has a special name, the coefficient. So for 7x cubed, the coefficient is, it's 7. For 4x squared, it's 4. Now what about for minus 3x? The coefficient there is -3. You've got to include the sign. And here's a tricky one. What if you just see x cubed all by itself? It looks like there's no coefficient, but there's actually a secret invisible 1 sitting right there, so the coefficient is 1. All right, now for arguably the most important piece of the puzzle, the degree. This is super easy. The degree of a polynomial is just the biggest, the highest exponent you can find. That's it. It's like its power level, and it tells us so much about how the polynomial will behave. So, looking back at our example, we have exponents of 3, 2, and 1. The biggest one is 3, so we say this is a polynomial of degree 3. Okay, so now that we know what a degree is, we can actually start giving these polynomials special names. It's kind of like how a biologist classifies animals. We're going to classify polynomials based on their degree. And this table lays it all out perfectly. If the degree, the highest power, is 1, we call it linear. You've probably seen those before. If the degree is 2, it gets the fancy name quadratic. Degree 3, that's a cubic, just like the example we've been using. And for degree 4, we call it biquadratic. See the pattern? The name is all about the degree. So, let's recap. We know how to spot them. We know how to take them apart, and now we even know their secret names. So, what's the point? What do we actually do with polynomials? Well, this is where it gets really interesting. We're going to talk about finding the solutions, the secret answers hidden inside. It all boils down to this one big question. Can we find a value for our variable for x that makes the entire polynomial expression equal to 0? Is there a magic number that does that? And the answer is absolutely. That special value, that magic number, is called a 0 of the polynomial. Sometimes you'll also hear it called a root. It's basically the solution to the puzzle. And trust me, finding these zeros is one of the biggest goals in algebra.
So how can you tell if a number is a 0 or not? Well, let's test one out. Let's take a simple polynomial. f of x equals x squared minus 1. And the question is the number 1 a 0 of this polynomial? Let's check.
The process is actually really simple. You just take the number you want to test, in this case it's 1, and you plug it in wherever you see an x. So instead of x squared minus 1, we get 1 squared minus 1. Okay, now just do the math. 1 squared is just 1, and 1 minus 1 is 0. And that's the jackpot. Because the answer is 0, we've just proven that, yes, x equals 1 is a 0 of this polynomial. It's that easy.
And this brings us to the big final question, doesn't it? It's one thing to check if a number is a 0 when someone just gives it to you, but how do you find the zeros from scratch, especially for a more complicated polynomial like this one here? Now that is the next big step in your algebra journey, and it opens up a whole new world of math. Thanks for cracking the code with me today.